Hi, today I will be presenting some information regarding the manufacturing process of injection molding and how to design and fabricate a mold that will produce a usable part. First, I'd like to discuss how injection molding works. Injection molding is a process by which melted plastic is injected into a mold cavity and cooled in the shape of a desired part. The machine that carries out this process is shown here and has 5 main components. First is the mold, held in place by the clamping mechanism on the left-hand side of the machine. A mold consists of 2 flat interlocking pieces of metal with cavities in the shape of the desired part. To inject plastic into the mold, solid plastic in the form of pellets are placed into the hopper, shown here, which funnels them along the grooves of this screw. As the screw pulls the barrel backwards, the pellets are pushed forward and against the heaters, which slowly melts them and pulls the liquid into the chamber in front of the valve right here. Once the desired amount of plastic has been melted and pulled in front of the valve, the screw reverses and pushes the barrel forward, pushing the molten plastic into the mold through the sprue hole. The plastic is allowed to cool, and then the clamping mechanism opens the mold, pushing the finished part out of the mold using an ejector rod shown here. Injection molding is very commonly used in industry because of its versatility. It is very easy to automate and uses non-destructive molds, making it a great candidate for mass manufacturing. It also allows for creating very complex and detailed parts. There are a very wide range of materials that can be used with injection molding, since there are a huge variety of plastics available with just as much variability in material characteristics. Some common places that you might find injection molded parts are in food containers, since they can be cheaply and easily mass manufactured this way. This process is also commonly used to produce medical devices, since the parts produced can be highly complex with very narrow tolerances and made from body-safe plastics. It's also often used in automotive and airplane manufacturing, since plastic parts can be designed to be much more lightweight than metal parts without sacrificing too much strength. For this project, and to demonstrate how the molds used for injection molding are designed and produced, I created a mold design that can produce a small toy piano. This mold was made out of 2 pieces of stock aluminum, each 4 inches long by 2 inches wide by 1/2 inch tall. The design I'm presenting today was created first using a 3D CAD model in SolidWorks, creating a toolpath in Fusion 360, and also in Fusion 360 converting that toolpath to G-code to be used to control the Haas mill. First, I created a SolidWorks model of my desired mold cavity design. As you can see, it's intended to create a small toy piano. The top image shows the bottom half of my mold, which makes up the base of the piano. The bottom image shows the top half of my mold, which contains the keys and buttons that are on a typical electric keyboard. Each corner of the cavity is rounded with a diameter of 1/8 of an inch, which is the diameter of the smallest tool that I'll be using to mill the cavity. The finished part should be 1.5 inches wide and 2.5 inches long. Shown here is an earlier version of my SolidWorks design, for which I had not yet added the rounded corners, which I'd like to show to discuss how I calculated the cavity volume. I used this version for ease of calculation, and I did this by calculating the volume of each known geometric shape and adding them up. Since the filleted corners would only subtract volume from the total, and I only needed to know the volume to ensure it was under a maximum limit, I decided that this was sufficient. Next, I created the toolpath simulation in Fusion 360. To do this, I first defined the tools that I would be using to create the cavity. I used a 1/4-inch flat end cutter to rough out the cavity on the bottom plate and possibly save a bit of runtime, and a 1/8 inch flat end cutter to cut the sections on the top plate since they were very small, and to finish the bottom plate cavity. Then I defined the edges of the cavity that I wanted the program to cut, which were the sketch outlines from my SolidWorks model. This is done using the 2D adaptive clearing tool in Fusion 360. A problem arose here with getting the program to cut sections that were the same width as the diameter of the tool on the top plate. However, this can be solved by changing the type of ramp. Helix ramping is typically desirable and safest on the tool, but for the very narrow sections like the black keys, I had to pick plunge to get the desired cavity width. Then from this information, Fusion 360 produces a simulated toolpath that will create the desired cavity. From there, Fusion 360 can be used to generate G-code that will instruct the Haas mill to follow the toolpath shown in the simulation. In this case, the program for the top plate in particular was very long and complex, much more so than the G-code that I produced by hand for the CNC machining project. It would have been difficult and time-consuming to read the entire thing, but from scanning the beginning and end of the program, it appeared to require limited adjustments, and the necessary changes were primarily personal preferences of Tim Goodner regarding how to start up and stop the Haas mill. If it were safe to complete lab activities in person, the next step would be to fabricate the mold. This would involve first bringing the G-code to the Haas simulator to ensure that there were not any errors in it. Then it could be loaded into the Haas mill, which would use the G-code to cut the cavity into the mold following the toolpath determined in Fusion 360. Next, the mold would need to be finished, which would involve cutting the sprue and fitting it with pinholes to hold the two plates together and hold the mold in the injection molding machine. Next, the mold could be placed in the machine and the part created. This demonstrates that a mold for injection molding can be designed and produced quickly and easily using these pieces of software. Fusion 360 is able to produce G-code that is highly complex and would otherwise be very lengthy and difficult or even impossible to write by hand. It also carries less likelihood of introducing catastrophic errors into the program than one written by hand. For example, a person handwriting a code could easily forget one line and end up not lifting the tool after a cut, breaking the tool, and ruining their workpiece. This and similar errors are much less likely to occur with computer-generated code. This process was quick and easy, even for a beginner, and I imagine someone with significant experience doing this could complete many mold designs in a day, making this process very appealing to manufacturers. Thanks so much for listening, and have a great rest of your day.